Our next speaker is Rod Pyle. He's an author, journalist, television producer, historian, and editor-in-chief of Ad Astra magazine. He has written 17 books on space history, exploration, and development, including Space 2.0, Innovation the NASA Way, Missions to the Moon, and Destination Mars. He has written for NASA's Jet Propulsion Laboratory that he'll be talking about today, Caltech, Wired, Popular Science, Huffington Post, Space.com, and other periodicals and websites. He's just really good with a keyboard or a pen. Rod also co authored and lectured for the Apollo Executive Leadership Program for NASA's Johnson Space Center and the Conference Board. So tell us what's new at JPL, Rod.
I would love to, and thank you for the extra breathy introduction. I haven't had one of those in a while. I like that. Uh, so this was an interesting project. It was book number 18 for me, and it's the third or fourth time I've done this for JPL. So they do a number of annual reports, and I've done two or three of the different ones, but this one in particular is interesting. It's got the very non-whimsical title of technical highlights fill in the year 2019, 2020, 2021. But it's a really cool book because it's about 80 pages, 85 pages, and about 30 to 35 stories of kind of their greatest hits of that year, if you will. And the hard part is going to these PIs or these chief engineers or whoever it is you're doing the story with and sitting down, and I try to give it an hour, even though I know I don't need that much time, because a lot of these people have been working on this stuff for a decade, and it's their life. So to go in, and I've seen some of the other media people do this, go in and say, okay, I got 10 minutes, tell me everything. And you see the heart drain out of these poor folks. So I give it more time, but in essence, what I'm really saying between the lines is, look, we got 400 words to tell your whole story. And so usually what happens is they start reaching for a dry marker and turning around to the whiteboard behind them, and the hands are shaking. It's like, no, 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 you need to use your words. So that's what the project is. It's short stories of some of the coolest things they're doing with a lot of pictures. So it's a graphics book, and the audience in broad terms is the general lay public, but the book is specifically printed and distributed to NASA headquarters, where the money pipeline flows from, and Congress and the executive branch, to say, we're still here, we're still doing cool stuff, keep sending the cash. So if I may screen share, I will go to, okay, my picture just changed dramatically. Can you see
We see your slides, but they are
JPL slide?
in, they're not in presentation mode
Right.
yet.
So let's change that. There we go. Should be
There
in
you go.
presentation mode now.
Looks great.
Very good. All right. So this is the sign outside of Jet Propulsion Laboratory in the lovely mountains of Southern California above Pasadena. It's always lists its address in Pasadena, although it's just kind of barely, it's actually in Flint Ridge, but we like to say it's in Pasadena because it's run by Caltech, as you can see just below the JPL sign there. Oh, this is my book commercial. That was what, 7 of the 18. I also the editor-in-chief of Ad Astra magazine. And if you have a chance, if you're not a National Space Society member, we're now selling these in 1,100 bookstores across the US and Canada. This latest issue is really fun for 2 reasons. I got to talk about the Chinese space program, which is something that interests me quite a bit. And I got to hire my cover illustrator to do this really cool cover, which I later found out wasn't completely original. I guess Time Magazine did something like this, but what I loved about it was who's first, right? So yeah, us and the Chinese. All right, so these are previous issues of this book. We always try to go for a strong graphic cover. And just a little bit about JPL. It's the only NASA field center that isn't actually managed by NASA. It's managed by Caltech. So it's founded in the 1930s. Founded, I use with quotes because it was a bunch of Caltech grad students firing rocket engines. They started on campus after one particularly unfortunate loud kabang. The Caltech campus said, you really shouldn't be doing that here. Go find somewhere rural to do it. So rural in Pasadena back in the 30s meant the Arroyo Seco, which is a big dry gulch just west of town. And it's still kind of a big dry gulch, actually. So they started firing off engines over there, and that's partially how Jet Propulsion Laboratory ended up being up at the top of the Arroyo Seco and nestled in the foothill of the mountains. By the 40s, they had to deal with the U.S. Army. They're making jet-assisted takeoff engines, which is where the jet and JPL comes from. And in the late 1950s, the United States was working on the Vanguard program to get our first artificial planet in space, which is what we used to call satellites. Unfortunately, the Soviet Union surprised everybody by orbiting Sputnik, and Vanguard exploded 3 weeks later on the pad. It was a civilian / U.S. Navy program. So the government came to Jet Propulsion Laboratory and said, hey, how fast can you guys get a satellite built and flown? And they said, I don't know, 3 months. Great, done. So they managed to get our first satellite up, Explorer, in 1958, early 1958. Then in the 60s, the whole planetary robotic exploration impulse really took flight. Some of you, very few of you actually, but people my age are old enough to remember the Ranger program, just barely, which was a series of probes flown to the moon. And the way to get close-up pictures of the moon was to fly into the moon. So you literally flew straight up and impacted the moon, and you got these great pictures of anything bigger than a dinner plate if you got close enough. But it took, of the, I think it was, I don't know, 9 or 11 Ranger flights, it took the first half of them to get past the failures, and then finally they're able to pull it off. And from there on, there was no stopping JPL. They started the Surveyor missions to the moon, the Mariner missions to Mars and Venus, and finally the outer solar system in the 70s and 80s. And it's about 6,000 to 9,000 employees. So if you work at JPL and you run into somebody in Southern California, they say, oh, do you know so-and-so? It's, you know, it's like any other largest. It's like asking somebody who's going to Boston University, oh, did you ever meet Jeff? You know, there's a lot of people at JPL. So generally the answer is no, unless they're particularly well known. But for instance, if you ask anybody who works at JPL, hey, do you know Rod Pyle? They'll say, who the hell is that? So here's a picture in the upper left of the campus.
I just want to jump in and so this rocket body that's about to smash into the moon, by no means the first of anything smashing into the moon, right?
No, we've smashed lots of things in the moon. The Soviet Union crashed Luna. It's either Luna 1 or Luna 2. What was particularly cute about that was they had made this, I think it was a beryllium ball. It looked like a soccer ball, and each of the little chunks that it would explode into had the sign of the USSR on it, the flag of the USSR. So the whole goal was to just scatter Soviet Union pendant pieces across the surface of the moon. It probably vaporized on impact, but it was a fun idea. So lots of things. Rocket stages smashed in the moon. We had the deliberate impactor from the, I think it was the L-Cross mission down near the lunar South Pole, because we want to see if there was water there. So if you make a big enough kabang, you know, you can analyze the spectra of what comes up. And in fact, in the early 60s, there were actually plans in both Russia and the US to detonate nuclear warheads on the moon. Why, you might ask? Well, the scientific impulse was, we can study the spectra of the explosion and get some idea of better idea of the composition of the moon. That's possible, but
And we
mainly
get
it
to
was
make a
just,
big boom.
yeah, mainly it was, look at us. We tower over you Americans, you know, and we were thinking the same thing. Fortunately, nobody did it. So yeah, the moon's been relatively unmolested in a major sense, but lots of smaller bodies have crashed there. On the right, you see the face of JPL from the early 70s. That has changed now. It's was one of the earlier NASA facilities to diversify after the Marshall Space Flight Center in the 1960s, which actually that was the impulse of Werner von Braun, who sort of pushed that program. Interesting man in so many ways. So let's jump into the meat of this here. Uh-oh, why isn't that working? There we go. Just one thing about the kind of people that work at JPL. This is from 1965. In the upper left, you see Mariner 4, first flyby of Mars by a spacecraft, took 22 grainy, low resolution pictures, about 200 pixels by 200 pixels, you see there in the lower left. And those images came back digitally. So it was a TV camera that was converted into binary and set back to Earth. Took about 7 hours to get each image. So you can see how our bandwidth has improved over the years. Well, the JPL people were impatient and they didn't want to wait for those black and white photo prints to come out of the lab dripping wet. So they took the printouts of the binary that came back from that image to the left there, or one like it, and cut those strips of paper out of the printer, cut that paper coming out of the printer into little strips and taped it up on the wall, ran down to the local art store and got some colored chalk and made this lovely drawing that you see this guy working on to the right here. That still hangs at JPL today. It's kind of one of those, little moments of miniature worship when you walk into I think it's in building 180, which is the main office building. It's very cool to see it, but it just shows the kind of people that work there. It's like, look, I can't wait around. An interesting minor tangent here. When the guys went down to the art store to pick up chalk, they told them what they needed, and they said, well, we either have blue and green or orange and yellow and brown, so take your pick. So had it gone otherwise, you might have had a first image of Mars being blue-green, but thank goodness that didn't happen. So this is the book this year, 2021 technology highlights. And those aren't cells to the left. Those are little ice crystals. This is a simulated picture, not a real one. We always try to use something kind of abstract for the cover because it draws in the interest of the reader, especially, we hope, Congress people, he said with his hands cupped over his mouth. And this is a picture of a sample being taken out at Europa. So we're soon going to have Europa Clipper, which is an orbiter. The whole idea is to sample some of the plumes that are coming up out of the surface, the cracks in the surface that we think are warm water that turns cold once it exits the planet's crust, and see if there are any organic compounds in there or other things of interest. So that little splotch in the left there that I just put an arrow on, we hope is a biomolecule. And the idea is if you scoop up a sample from orbit and analyze it, you can find a biomolecule, which sounds pretty cool. I mean, that's a very smart way to go about it. You don't have to land on the moon and drill through the surface or melt through the surface or scrape things up. You just fly by and grab something. But of course, because this is space exploration, it's not that easy. And I apologize for this one. I only had one image, which is the one out of the book. Whoa, where did that come from? Hold on a second. My spreadsheet opened for some reason. So each of these, I'll start with a need. So what was the need here? Well, we wanted to gather samples from the plumes of Enceladus or Europa. So you've got ice particles spewing from cracks in the surface, and it sounds easy. You just want to fly through them with a scoop and pick them up. How do you do that? Well, you're scooping at orbital velocity, but what is that velocity? It turns out that velocity is critical. So JPL has been working on software to try and figure out what the proper speed is. So you've got biomolecules, you hope, present in these inside the ice crystals. And that's a little computer simulation up there on the left of what happens when you grab an ice crystal and you've got amino acids in it. And the crystals are being drawn into the scoop or hitting the scoop at hypervelocities and literally vaporize in a femtosecond. Now, if it's done at the exact right speed, if there's any biomolecules in there, they ionize and then you can see them. But if you're going too fast, the crystals fragment and destroy that process. If you're going too slow, the biomolecules may fail to ionize. So this is the kind of thing that specific departments at a place like JPL agonize over. So what's the sweet spot here? Well, I'm not going to show you the calculation because we've only got a short period of time together, but it turns out, just in case anybody asks you at your next party, it's 1.8 to 3.7 miles per second, which is good to know, because otherwise, if you go up there and you don't do things properly, you're definitely not going to get an indication. And by the way, if anybody remembers the Viking project to Mars, those were two orbiters and landers from the 1970s that arrived and landed in 1976. That's kind of an example of a good idea that didn't quite work out. So the Viking landers carried a life science package it was as clever as could be for the time, but those life science detection experiments were based on life as we understood it at the time on Earth, which is basically, hey, let's scoop up some dirt, we'll inject some nutrients and some water in it and watch what happens. And in 3 out of 4, very little happened. In the fourth one, there was a reaction, but apparently it was chemistry, not life. So the more you can figure out how to do these things properly before you leave Earth, obviously the better. So this is sort of the state of the art of what we hope would be life science at Enceladus and Europa. Next story, to boldly rove. So we all know about the rovers on Mars, the Mars exploration rovers, Curiosity and Perseverance. These are the flagship missions. They're big, they're billions of dollars, they do great things, but they're very slow and you have to be really careful with them because they're expensive. And ever since the end of the MER missions, where we had Spirit and Opportunity on Mars, we now only have one at a time. And you don't want to risk them, right? So the idea behind these mini rovers is to use them as add-ons to the large rover. So here's a picture of one trying to work its way over a fairly small rock. These are lightweight on Earth. They're really lightweight on Mars, which is only a little over 30% of Earth gravity. So they can scamper around pretty effectively. So the idea is to have a bunch of these loaded up in the back of a rover. If anybody's ever seen a World War II movie, it's almost like the way depth charges eject off the back of a destroyer, right? So Perseverance goes somewhere interesting. It sees a crevice or a cave or a rock overhang or something, ejects one of these things out of the back. It unfolds once it hits the ground and skitters off. They've got a fairly simple instrument package because they're small, but if you got cameras and a spectroscope and a few other things, probably no sampler, that's pretty good. Because if you get down a cave and you see a little 6-legged green thoat down there waving at you, then you just made a really worthwhile discovery and it didn't cost you much. So one of these is called Puffer, and it was developed originally by a grad student at UC Berkeley. And here's some of his early work. That thing that looks like a Terminator or a transformer, excuse me, in the second photo down on the left is actually a folding fabric circuit board. So you have the wheels on these folds on the sides of the circuit board. So the thing could store flat, and then once it hits the ground, it actually unfolds and drives around a little tail hanging down the back. And there's an early prototype there on the right. These are between hundreds of thousands and maybe $1 million each to build, which still sounds like a lot. Could be less with off-the-shelf componentry, but compared to a full-size rover, it's nothing. So here's a smaller second-generation Puffer next to a quarter. You can see how small they are. And the latest iterations of this are autonomous, which uses AI for some interesting things I'll discuss in a second. These 4 pictures to the right here, laterally 1, 2, 3, and 4, you can see that once a Puffer has popped off the back of the rover and unfolded, if it drives over a crevice that's really got low clearance, it can refold its wheels, if you look at picture number 3 here, and actually be almost flat when it crawls into these cracks and crevices. So this is exploration on an exponentially cooler scale than you can do with a rover the size of a Mini Cooper, right? Because now you can go anywhere and do just about anything. And if you lose one of them, we'll just send another one after. That's a close-up of it crawling into a crevice. It looks kind of pathetic this way, but it actually is very cool. So as I said, they're low mass. They can go into all kinds of places the bigger rovers can't do. And then we're particularly interested in caves and caverns and pits on Mars. This may be a bit under the task of getting into a large crater or pit, but for smaller ones, it might be able to drop in over the side. But the point is, when you get into these covered areas, they're protected from radiation and they moderate thermal extremes. So there's a chance, especially in the volcanic regions, if there's some geothermal heat coming out of Mars, which it appears there is from the latest work that InSight has been doing, there's a chance that there's going to be microbial life down there living with water vapor, a source of water vapor. So, this may not be the exact right probe for that. That's going to take some thinking, but the further in you can go to these little dark and scary places that the big machines don't want to go, the more at least leading indicators of things there that you might want to be able to see. So it can survive, we think, a 10 to 15 foot fall on Mars, again, with the lighter gravity. And as I pointed out earlier, at least on some of the prototypes, the circuitry is printed on a fabric substrate, so they're fairly flexible. And by the way, each of these projects has some commercial applicability. It's a longer story to go into how that process takes place, but JPL and NASA, as you all know, are very, very generous with their data, share most of it with the world, unless it's something that has particularly secured national security implication. And so it's not only good for commercial companies in the United States, but really for people all over the planet. Bigger is better. What am I talking about? Well, I'm talking about apertures. So we've just seen the James Webb Space Telescope go up. Magnificent mission so far, but boy, you want to talk about a white knuckler with over 400 individual functions it had to perform to unfold and clamp and get ready to do its business out there a million miles from Earth. I don't know about you guys, but when I saw the design for that mission, I had the same reaction I had when I first saw how Curiosity was going to land, which was kind of a, what were you, is this really the simplest way to do this? Well, when you've got a big space telescope that's got to fly on small rockets, it is the simplest way to do it because you've got to fold everything up, and it's a major do and makes it very expensive. So how can we get around this? Well, one way is to use a synthetic optical aperture. You've probably, most of you heard of synthetic aperture radar. This is a synthetic optical aperture, which works in a different way. Space telescopes are the future of astronomy. The more junk we get in orbit, the harder it is to see things out beyond. So increasingly, we think space telescopes are going to be more and more important because they not only are able to fly above all the junk in orbit, but they also bypass limits of the atmosphere and are better at observing infrared and even ultraviolet, because the atmosphere tends to make that difficult. And there's also just pollution along with refraction. So for a lot of reasons, we like space telescopes. So what are the constraints? Well, as I said, the large ones like Webb are complex and very expensive to fly. And a current rocket fairing, even on the Falcon Heavy, is limited to about 15 feet in diameter, maybe 25, 28 feet in length. So you've got to pack these things up in a fairly small package. And that's about the maximum size you've got to launch at this point, at least until Starship's flying. So what's the answer? How about rotating synthetic aperture telescopes? So this is a close-up of the experimental unit. That's just a regular old camera lens there. That little white stripe is a strip, if you can use your imagination a bit, that represents a mirror about 15 feet across and maybe a foot wide. So basically, you've got in the ultimate design of this, you've got this big single strip of a mirror, and you take multiple exposures, rotating that thing, and then you build those exposures up by overlapping them and processing them, and that gives you the equivalent of a 15-foot diameter mirror. So if that strip was, say, 2 feet wide and 30 feet tall and did that rotational process, you now have the equivalent of a 30-foot aperture telescope. So you can see that you're getting a lot of bang for your buck here. And this experimental version was made with off-the-shelf components, by the way, but it hasn't flown yet. And it only has to rotate through 180 degrees. It doesn't have to do a full 360 because obviously you're on both sides of the central pivot point. In the estimation of the designer, it could lead to 100 meter or 300 foot wide instruments. That's a bit of a do, that require very large rockets or some unfolding, but compared to Webb, it would be quite simple. So here's a sample image. On the left is the moon through the first take with that little tiny synthetic aperture rotating SLR lens that I showed you. And to the right is the processed image. So the example here, it's still fairly low res, but it does give you at least an idea of how you can get something for nothing out of image processing. And it's getting better every day. And because we like to save money at NASA, here's the camera they used to test it. So instead of building some big expensive bespoke rig, they just used a standard off the shelf SLR with that little tiny aperture in the lens. But at least in principle, it works. And this could lead to real huge breakthroughs in optical astronomy off Earth for a relative pittance. On the other hand, sometimes smaller is better. What's this funny looking thing? Looks like a pepper grinder. It's actually an atomic clock. So we like atomic clocks because timekeeping on spacecraft is really critical for navigation. You've got to have accuracies down to a billionth of a second, not because we just like to know what time it is, but because when you're flying all the way out someplace like Jupiter or Saturn, if your timekeeping and navigation is not spot on, you could be hundreds of thousands of miles, if not more, off, and you want to be a lot closer than that. Atomic clocks of the accuracy of the one I just pictured have results in billionths of a second, which results in a delivery within a yard of what you're aiming for out there, which is the thickness of some of the rings of Saturn. So that can be kind of critical because you don't want to run into those things. Now, the systems we've been using on the
It's
ground
interesting
were
that you
large and power
chose
hungry.
it's
Sorry?
interesting you chose to call it a yard instead of a meter.
Well, so yeah, everybody there says meters, but because I write for the lay people all the time in the United States, I use yards and feet. And
Yeah,
I
yeah.
personally still have a little trouble converting in my head, I have to confess. But just so it's said in the magazine, we say imperial and then metric, but yeah, I do tend to use
Yeah, it
yards.
goes a long way. It just really illustrates your mode of thinking, the level of expertise that you have in all of this information, and then compounded by your ability to translate it for a lay audience is really spectacular.
That is a very generous assessment. What you might also say is he grew up in a time of non-metric units and never bothered to learn metric. But I like your interpretation a lot better. So thank you. Uh, so atomic clocks can be big, heavy, and really power hungry. And it was hard to build them to fly. And you ended up having all the hardware on Earth. And now you're tying up the Deep Space Network, which is NASA's a series of radio dishes distributed around the Earth in 3 points to do all this navigation from the ground. That's about as small as they get on the ground. This thing is a little bit bigger than a sugar cube, and it uses, it's called a micromercury trapped atomic clock, and it basically has particles bouncing back and forth that you can measure the travel rate of with an optical sensor. And here it is next to a sugar cube on the left. So you can see it's pretty darn small, and its power requirements are minimal. And
Tasty.
power is everything in space, as you may remember from Apollo 13, because power supplies are big and bulky, and whether they're solar panels and or batteries and or atomic in nature, they have a lot of mass, and you want to use that mass for instrumentation and experiments. So if you can keep the navigational and propulsion technology small, that's very helpful. So this is a little bigger than that measurement's a little off. It's closer to 3/4 of an inch, but it's 1,000 times more accurate than the current model, which is down here. That was about 6 years ago. It was about 1.5 feet long. So you can see the comparison of the new one over there. And it's 1,000 times more accurate. So when I'm writing these things, they throw around these numbers like, oh, it's 1,000 times or exponential or, an order of magnitude better. At a certain point, that almost becomes meaningless. So it's like, this is why sometimes NASA comes up with silly infographics. I don't know if you remember it, but there was a video infographic done on SLS of how many elephants worth of propulsion it was putting out with these elephants spilling out the bottom. That one's kind of infamous, but it does give the public, the general public, an idea of what's going on. And frankly, when you're dealing with Congress and you send this wonderful, polished, expensive book to them, it usually goes to congressional aid and ends up becoming, reading in the men's and ladies' rooms or something. So you want to make it as accessible as possible. So in this case, we just say it's 1,000 times more accurate the current model, which means you can get to a meter within where you want to go, roughly, which is great. And because there's less mass, you can fly longer missions with less fuel and more mass used for instrumentation. And here's just a graph of how these things work. it's beyond my pay grade to really fully explain it, but you've got these mercury ions bouncing back and forth, and you measure them with a photo multiplier, and then somebody makes sense out of that. Now, speaking of navigation, here's, I think, one of the coolest things I saw this year. Current spacecraft tend to be navigated from Earth. They're guided from Earth. They have star sensors on them, which is basically just a photocell pointing out where we hope a star like Canopus is going to be. But to navigate that way can be tricky. It can be easy to lose that star signature. It ties up time with the deep space networks. And when you're getting out to the outer solar system, the delay time of radio going back and forth can be substantial in the many hours. And the star trackers are difficult to keep aligned sometimes. So JPL has been working on a project to use high frequency pulsars as essentially lighthouse beacons. And these are rotating neutron stars that are spinning out a lot of radiation from their poles. So they blink and essentially look like lighthouses out in space. Now, they don't move around, right? They're really far away. So in particular, we're interested in millisecond pulsars that emit radar frequency, X-ray frequency. And this was actually derived from technology used on Perseverance's pixel X-ray camera. And they realized they could use the exact same components to do tracking of these X-ray pulsars. So again, it's kind of a complicated technology tale, but basically you've got an X-ray source and this device called a polycapillary device, which uses millions of tiny glass tubes to focus down the X-rays because they behave differently than optical light. And then you've got the little sensor on the back. But the idea is that when you combine this with artificial intelligence, you've got spacecraft that can effectively self-navigate for long periods of time. So if you're getting out beyond the solar system where the Voyager 1 and 2 spacecraft are now, you just cut them loose. You let them off the leash and say, okay, Rover, go find Alpha Centauri, do your thing. And they're able to do that. And you just do check-ins periodically. But part of the advantage here, as I was pointing out, is you're not tying up the deep space network with this constant conversation with distant spacecraft. If you ever have a chance to go over to Jet Propulsion Laboratory and stand in their control center, they have this really groovy, big view screen up front that looks like it's out of the Starship Enterprise, that has all the different tracking stations and the chart of the signals going up and down. And it changes spacecraft every few minutes or every hour or so. But they're constantly rotating through, and NASA's flying a lot of stuff. The European Space Agency is flying a lot of spacecraft. We work with them on a lot of things. So you're constantly having to, it's like watching your father after he had had 3 beers skipping between sports channels on Sunday. It's not the ideal way to navigate spacecraft. So if you can get them to have more and more autonomy, that's a good thing. So this image on the right here is a solar sail heading way out beyond the solar system with a very foreshortened beam looking at a pulsar. So like I said, you combine that with AI, and now you really got something. How much time do I have left?
About 5 minutes, but we can go over just a little bit.
Okay. I may
Uh,
have to skip the last module, but I'll get as close as I can.
okay.
So what's the need for getting small spacecraft in orbit around other planets and moons? Well, we need fuel and mass efficient ways to enter those orbits. As early as the 80s, we were experimenting with aero capture, which is where you have a spacecraft heading, in that case, to Venus, and you dip into the upper atmosphere just enough to slow it down. Because if you don't do that, you have to have a great big heavy rocket engine with lots of heavy fuel to effectively break it into orbit. So we're very interested in finding ways to do that don't require as much mass. So traditionally, for spacecraft at Venus and Mars, when we've done aerobraking, we just have the spacecraft configuration as it is, which is usually with the solar panels feathered back a bit. And it just barely touches the upper atmosphere enough to slow it down over the series of many months or a couple of years, which is great, but it's not as efficient as it could be. So here's an example of the difference when you have to break into an orbit. In the upper left, you've got Mariner 7, which is a flyby mission to Mars. fairly Spartan spacecraft. In the lower right, you have Mariner 9. So Mariner 7 was under 1,000 pounds. Here he is with the Imperial units again. Mariner 9 was over 2,200 pounds. The main difference, besides slightly better cameras, was all that fuel mass so that it could break into Martian orbit. So obviously, if you could do that without rocket engines and gas tanks, that's a good thing. So this is Mars Global Surveyor in a very speculative, nicely imagined image of it doing aero capture with those little speed streaks going to the right. It worked well, but in this particular case, one of the clamps on a solar panel had some issues, and it made this very tricky. The spacecraft still worked, but it could have easily been lost. So when you're dragging your foot effectively in the upper atmosphere to try and slow down a bit, solar panels are delicate things. So we'd like to have a way to do that. It's a little bit more robust, but not very heavy. Now new designs, because technology is becoming so miniaturized, even with off-the-shelf components, they're a lot smaller, and that makes it a little easier to slow down because you have a lot less mass. And if you get your drag right, this can become a pretty efficient process, but there's still a better way. Now, we've currently got about 24 deep space probes in operation. Some are very large, some are just kind of large. They're all big and expensive, though. So for future missions, we'd like a lot of them to be CubeSat sized. I think this is a 3U CubeSat, if I remember correctly, or thereabouts. And much smaller mass and using as much off-the-shelf equipment as possible. So the idea here with this project is to use a drag skirt, which is basically just an umbrella made out of a strong fabric that deploys as you're getting near the body you want to slow down around. And it creates a lot more atmospheric drag while effectively protecting the spacecraft at the same time. It's really light. It's not terribly difficult to deploy, although the people that designed the antenna on the Galileo Jupiter probe might offer some argument about that. But there's a bunch of reasons that had problems, and should work and would allow you to carry a lot more science equipment on a much smaller package. So finally, I'll close with combating climate change, because I saved the hot topic for last. We need better detection of greenhouse gases on Earth to continue trying to fight climate change. Now, the way that we spot them today mostly has been done by high altitude aircraft and drones. You can get data from orbit, but it's not as exact and granular as we'd like. And if you really want the best indications, you need to fly over it at moderately low altitudes. While that's expensive and you can only do it every now and then, methane is one of the most important gases to track, and it's also very hard to detect. Here's a picture of a methane plume from an industrial source. So what we want is smaller, more accurate sensors that can give us global coverage, as we see here with all these hotspots, with a lot of frequency. How do you do that? Well, image spectroscopy has been picking up a lot of speed at JPL in particular over the last 20 years. It's good for a lot of things. One of the things it turns out it's good at is spotting methane, but you need really sensitive diffraction gratings to create that spectra. How do you make those? Well, JPL has the answer. They have a thing called the Micro Devices Lab, where they actually print diffraction gratings using an electron beam. So they used to be etched with mechanical tools. Now it's printed at nanoscale, so you can see the kind of scale we're talking about at the bottom there. These are in nanometers. So they may look a little rough and bulky, but they're really small. And this process is so exacting, it makes my brain hurt every time I go over there and look at it. And so you etch these things with electron beams. And now you can essentially, which is what they're doing at this project called Carbon Plume Mapper, you can build 20 satellites, have them flying in polar orbit, and you get global coverage 24/7 of these methane plumes and eventually other gases. And the plan is to have this going by 2024. That's a picture of the Carbon Plume Mapper. It looks like a garbage disposal, but I promise it's much fancier. And this will give us fairly granular coverage of methane emissions from all sources: agriculture, meat production, landfills, petroleum extraction, and other industrial sources. And once you can spot them, you can start getting more exacting about how you're going to mediate these things and begin to turn down, if you'll pardon the pun, turn down the gas a bit on climate change. So as I said earlier, most of these are shared freely with industry around the world. And this is one of the value propositions of a place like NASA and JPL in particular, is all this great stuff they're working on is available to the world for use. The full report, this book will be available in late March. If you go on the web and search JPL Technology Highlights, if you want to read it, the last, I think, 7 years are there. And as I said, this one will be posted in March. That's my commercial for my books. Thank you very much for listening. And do we have time for questions?
Sadly, no, but you answered so many just through your talk.
Well, thank you.
And, I still have questions that I wrote when you were here the first time that are in the kitty. So I think we'll have you back sometime and just do all the Q&A that's pent up.
I'll try to talk less next time.
No, keep talking more. You've got a lot to share. Thank
Thank
you
you so
so much,
much.
Rod.
Pleasure.
All right.